The first one here goes pretty quickly, actually. Our base matrix will be 3, 2, 2, negative 1. And we cross multiply, or we find the determinant. We get negative 3 minus 4, that equals a negative 7. That's the base matrix determinant. For the X matrix, we have 7, 0, 2, negative 1. So that determinant will be negative 7 minus 0, or negative 7. And for the Y matrix, 7, 0, 2, negative 1, giving us negative 7 minus, oops, sorry. Let me try that again. I got that backwards. For the Y matrix, we got 3, 2, 7, 0. That looks better. Giving us 0 minus 2 times 7 is 14, is negative 14. So now for our values, X is negative 7 over the base of negative 7, which is 1. Y is negative 14 over the base of negative 7, which is 2. So the solution to this system is 1, 2. Well, for number 2 over here, it's going to be a little more complex for our base matrix. 2, 3, 1, negative 1, 2, 1, 3, negative 5, negative 1. It's 3 by 3, so we're going to have to bring over the first 2 columns. Doing our down diagonals. 2 times 2 is 4, times negative 1 is negative 4, plus negative 1 times negative 5 is 5, times 1 is 5, plus 3 times 3 is 9, times 1 is 9, giving us 10 for the down diagonal product. Going up, 1 times 2 times 3 is 6, plus 1 times negative 5 times 2, negative 10, plus negative 1 times 3 times negative 1 is 3, giving us a negative 1 for our up diagonal product. So our determinant will be 10 minus a negative 1, or 11. So the base matrix is an 11. Now let's do the X matrix. We get the constant 7, 8, 4. The Y values, negative 1, 2, 1. Z's, 3, negative 5, negative 1. And of course, we rewrite those first 2 columns. And we'll do our diagonals. So going down, 7 times 2 is 14, times negative 1 is a negative 14, plus negative 1 times negative 5 is 5, times 4 is 20, plus 3 times 8 is 24, times 1 is 24. I believe that adds up to 30 for our down diagonal total. Going up, 4 times 2 times 3 is 24. Plus 1 times negative 5 is negative 5, times 7 is negative 35. Plus negative 1 times 8 times negative 1 is just 8, giving us, I believe it's a negative 3. We get a determinant of 30 minus a negative 3, which is 33. For the Y matrix, we have the X values, which are 2, 3, 1. Constants of 7, 8, 4. And the Z's of 3, negative 5, negative 1. Rewrite the first 2 columns. And we'll do our diagonals. Going down, 2 times 8 is 16, times negative 1 is a negative 16, plus 7 times 5 is, or 7 times negative 5 is a negative 35, times 1 is a negative 35, plus 3 times 3 is 9, times 4 is 36, gives us a negative 15. Going up, 1 times 8 times 3 is 24, plus 4 times negative 5 is negative 20, times 2 is a negative 40, plus negative 1 times 3 is negative 3, times 7 is negative 21, which is, what was that, negative 37 for the up diagonal. So our determinant is negative 15 minus a negative 37, which is a positive 22. And then let's do our Z matrix. We have our X's, 2, 3, 1, our Y's, which were negative 1, 2, 1, and our constants, 7, 8, 4. Recopy the first two columns. I did something backwards there, didn't I? Oh, 2, 3, 1 is right. And let's do our diagonals. 2 times 2 is 4, times 4 is 16, plus negative 1 times 8 is negative 8, times 1 is negative 8, plus 7 times 3 times 1 is 21, which that adds up to, I believe, 29 for our down diagonal total. Going up, 1 times 2 times 7 is 14, 1 times 8 times 2 is 16, 4 times 3 times negative 1 is a negative 12. That gives us 18. So our determinant is 29 minus 18 is 11. So X was the X determinant of 33 over the base matrix determinant of 11, which is 3. Y was the Y matrix determinant of 22 over the base matrix of 11, which is 2. And Z is the Z matrix determinant of 11 over the base matrix determinant of 11, or 1. So the solution here, X is 3 when Y is 2 and Z is 1. Any questions on those? Okay, so today I want to take a look. What happens when we have a system that looks like this? (5x plus 4y equals 5). 3x minus 2z equals 19. And 2x minus 5z equals 4. Now looking at this, it does not really fit our standard form. It is not in that form of x's, y's, z's equals constants. But we can change it. We can put it into that form rather easily. The first equation will become 5x plus 4y plus 0z equals 5. Next one, there's no x. So put in 0x plus 3y minus 2z equals 19. Next one we have 2x, but there's no y, so plus 0y minus 5z equals 4. And now we can do our matrices. Our base matrix, 5, 0, 2, 4, 3, 0, and 0, negative 2, negative 5. Recopy the first columns. And we'll do our diagonals. 5 times 3 is 15, times negative 5 is negative 75. 4 times negative 2 is negative 8, times a positive 2 is a negative 16. And 0 times 0 times 0 is 0, giving us a negative 91 for our down diagonal total. Going up, well, 2 times 3 times 0 is 0. 0 times 2 times 5 is 0. Negative 5 times 0 times 4 is 0. So this determinant is just a negative 91. So let's do the X matrix. We're going to do the constants, 5, 19, and 4. 4, 3, and 0. And 0, negative 2, and negative 5. We'll recopy the first two columns. And we'll do our diagonals. Well, 5 times 3 is 15, times negative 5 is a negative 75. 4 times negative 2 is a negative 8, times 4 is a negative 32. And 0 times 19 times 0 is 0. That's actually a negative 108. Or 107, sorry. Negative 107. Going up, we have 4 times 3 times 0 is 0. 0 times negative 2 times 15 is 0. We have negative 5 times 19 times 4 is a negative 380. So we have negative 107 minus a negative 380. We plus a positive 380, 273. Let's do the Y matrix. We'll have the 5, 0, 2. Put in the constants, 5, 19, and 4. And the Z's, 0, negative 2, 5. Recopy the first couple of columns. And do our diagonals. 5 times 19 is 95, times a negative 5 is a negative, is that 475? Let me double check that one. It is negative 475. Plus 5 times negative 2 is negative 10, times 2 is negative 20. And then the next one is 0 times 4 is 0. That's a negative 495 is that down diagonal total. Going up, 2 times 19 times 0 is 0. 4 times negative 2 times 5 is negative 40. And negative 5 times 0 times 5 is 0. Giving us negative 40 is our up diagonal total. Something doesn't feel right there, but that's okay. Oh, seems to work. Okay, so get back here. We've got oh, come on now. I got my stuck in footnotes. There we go. So that gives me negative 495 minus a negative 40 So again, that's plus a positive 40, which is a negative 455. Is that determinant? So I have to do the z's. So we've got 502 for x. For y, we've got 430. And for our constants, 5, 19, and 4. So then we'll do 502, 430. Rewrite those first two columns. And then we're ready to do our diagonals. 5 times 3 is 15, times 4 is 60, plus 4 times 19 is 76, times 2 is 152. I'll double check that one quick. Yep. And 5 times 0 times 0, of course, is 0, so that is 212. Going up, 2 times 3 is 6, times 5 is 30. Well, 0 times 19 times 5 is 0. And 4 times 0 times 4 is 0. That's 30 going up. So we have 212 minus 30 equals 270. 272, is that right? Nope, 2. What am I getting wrong? Missed a negative somewhere, didn't I? Nope. 282, it looks like, is what I'm getting there. Or 182, that's better. This is what we get there when we subtract. So now, x is the x matrix determinant of 273 divided by the base determinant of negative 91. This is a negative 3. Y is the y matrix determinant of negative 495 divided by the base matrix determinant of negative 91. It's a positive 5. And z is the z matrix determinant of 182 divided by the base matrix of negative 91, giving us a negative 2. So x is negative 3 when y is 5, and z is negative 2. So you can see here it's almost easier to do with those missing variables because of all the zeros. When you're doing your cross products, your diagonal products, I should say, not cross products. When you're doing your diagonal products, any diagonal that has a 0 in it is going to be a 0, so you don't have to multiply it out. So it actually saves you quite a bit of work. Whereas with elimination or substitution, it'll save you a little bit of work, but with the addition elimination method, it almost makes it harder because one of the variables won't cancel out. Now we can get into larger systems of equations. We're not going to in this class. But the reason I wanted to show you the matrices is the matrices, a matrix is how we do things electronically. For example, I'm going to show you a 4-variable system. I'm not going to make you solve it, and we're not actually going to solve it by hand. So let's make one up here. 5x plus 3y minus 2z plus w will be our 4th variable. What is that? 10s. 2x plus 3y plus z minus 2w equals 2. And 3x plus y minus z plus 5w equals 7. 2x plus 2y plus 2z plus 3w equals 11. Now, this system of equations here, we could solve it, but remember, what we would have to do is we'd have to reduce it to, if we're going to do like z here, we can see the z variable would actually be pretty easy to get rid of by doing addition. But what we would have to do is we would have to use each of the equations, well, 2 of the equations would have to get used twice. We'd have to get 3 equations with only 3 variables left, and then we'd have to solve that 3 variable system. That's a lot of work. Or we could use the matrices, but remember, a 4 by 4 matrix, we can't use the diagonal method. We have to use the partials. But because of the matrices, we can use electronic means on this. I'm actually going to put a matrix into the graphing calculator here, and there's several programs, computer programs out there that use matrices like this. I'm going to create a matrix. Now this has 4 rows. I'm going to give it 5 columns. The reason I'm doing that is the calculator wants me to put in the X, Y, Z, and W column, but it also wants me to put in the constant column so it knows where to put that matrix in the other, it has those values to put in the other matrix other than the base matrix. 5, 3, -2, 1, and 2. 2, 3, 1, -2, 3, 1, -1, 5, and 7. 2, 2, 2, 3, and 11. So there's the matrix with all our values in it. And the command on this calculator is RREF. That stands for Reduced Row Echelon Form. So we're going to do that with the first matrix, the one we just created. And you can see it gives us a solution matrix. This one here is in the X position. That's saying this is the solution for X. This one here is in the Y position, saying that's the solution for Y. This one's in the Z position, saying 3 is the solution for Z. This one is in the W position, saying 1 is the solution for W. That gives us the solution, 2, -1, 3, 1. Now, like I said, we're not going to force you to do any of that in here, but I wanted you to see the point of doing the matrices. I mean, there are some systems that are easier to do by hand with the matrices and Cramer's rule. But the matrix, a matrix is how we communicate with electronic devices. In construction, there are wind shear matrices and stuff like that for buildings that engineers use to calculate the loads and to quantify the stresses on a wall to analyze it, and something similar to this. Obviously, a little bit more complex program what the graphing calculator has. In materials, they do the same thing. They have material property matrices that get used to understand if the material can hold up to the different forces. It might have a tension force stretching it, but then it also has a torsion force that's twisting it. And so, like analyzing a metal beam and things like that, they would have a force matrix or a characteristic matrix to analyze it. Okay, the good news, since this stuff is kind of difficult, I wanted to give you an easy day today. No new homework today, so just a little chance to finish things up. But there is a quiz out there. The quiz is actually, I believe, assigned on Monday on matrices and Cramer's rule. That if you get a chance, you should start working on that. Like I said, no new homework today, so that is it for this week. We'll give you guys a little bit of a light weekend. Remember, if you are missing any homework, we have until next Thursday. And December 17th is the drop dead date. Look in Blackboard. In the grade book, the cutoff, I always say 80%, but technically it's 79.5%. Now, if you hit 79.1, I'll round you up. But you've got to be in that 79 to 80% range to pass this course. The reason for that, you'd still pass with like a 70 would be a D, but because you guys have a class next semester, another math class, you have to have a C or better in this class, which means 79.5. So look at your grade in Blackboard gradebook. If you are below that, you need to go back, check first and see if you're missing any assignments, any grades. So look for one, any missing quizzes or tests. And the second thing you can do is you can do corrections on low scores. Especially, I mean, you're welcome to do corrections on any assignment, but especially tests. I mean, let's say you got an 80 on a test and an 8 on a quiz, 8 out of 10 on a quiz. Well, both of those are a C. But if you do corrections on the quiz, you get back half your points. You'd get back 1 point. You do corrections on the test, you'd get back 10 points. So several of you have tests sitting out there in the 70s and 80s percents. Do corrections on those. What you would get back in corrections could be worth as much or more than a full quiz. So make sure you're looking at those. We have 1 week from today to do that. With that, I'm going to let you guys go for the day, actually for the week. If you have any questions on stuff, on doing corrections or missing assignments, let me know. Otherwise, they are dated in the grade book, so you can look in the course information and find the folder for the correct date and find your missing assignment if you need it. If you do submit those, please let me know so I can go back and make sure they get graded and in the grade book. Anybody have any questions?